All right, so I'm going to continue to talk about this intimate relationship between aerosols and climate sensitivity. Steve and Chris stole some of my thunder, but that's okay, I think, because this topic's important enough that we can hear about it a few times. The economists in the room may recognize some economists here in the co-author list here. And so towards the end of my talk, I'll get to collaborative project that we've done with support of the YCEI. But before that, I'll talk about generally how aerosols can affect climate, and then move on to talk about this relationship between aerosols and climate sensitivity that we've already heard a little bit about earlier today. And then I'll talk about this new approach that we've taken. And I look forward to having feedback on those very recent results. All right, so I thought it would be appropriate in the Geology and Geophysics department to start by talking about the effect that we saw from aerosols emitted by the volcanic eruption from Mount Pinatubo in 1991. And I think it's a very nice example of how powerful aerosol effects on climate can be. This is a study by Brian Soden and co-workers in 2002. So the top here, let's see. Yeah, the top here, we have observations in black and 3 realizations of the GFDL model. And this is showing the cooling as a result of the eruption, which is, the eruption is indicated here on the timeline. And you can see that we got a cooling from that eruption, from the aerosols that were emitted from the volcanic eruption, of more than ½ a degree C. And that cooling persisted for several years. And the reason it could do so was that the eruption was so explosive that it put aerosol particles all the way up to in the stratosphere, where aerosol particles can have long lifetimes in the atmosphere. This study was also a nice test of one of the major feedback mechanisms in our climate system, the water vapor feedback. And Soden and co-workers could test their model compared to observations here for column water vapor changes in response to the cooling and also upper tropospheric water vapor changes. And it appears that this model, anyway, got the water vapor feedback right, and that water vapor feedback was central in reproducing the cooling from the volcanic eruption. Now, zooming out quite a bit, we have the temperature record for the last 150 years or so, and I've indicated that cooling from Mount Pinatubo here, it doesn't look as impressive in this temperature record. What you can also note is the so-called hiatus, which I believe the next speaker will talk more about. That hiatus goes away when you look at decadal averages instead of annual data, as we have on top here. And you can argue that looking at decadal averages is perhaps the appropriate thing to do for climate change, for the scales that we're interested in. What doesn't go away, though, is this hiatus from the 1950s to roughly the 1980s. Or you could even argue that there was a temporary cooling at that time. And we think that that was related to the amount of aerosols that we were emitting into the atmosphere at that time. So we can look at indirect evidence for that being the case. We can look at the part of the radiation spectrum that aerosol particles influenced. So what I'm showing here is for different time periods and for different parts of the world, I'm showing trends in downward solar radiation at the surface as an indirect evidence that the cooling was caused by aerosols. So you see that from the 1950s to the 1980s, when we had this period of cooling, that coincided with this period of so-called global dimming, where we had a downward trend in incoming solar radiation at the surface. Then around 1980, we had this transition to what has been called global brightening, at least in the US and in Europe. You can see that the global dimming continued very much in parts of Asia. And then after the 2000, the brightening has continued, but in China, there's now dimming again, and the dimming in India has also continued. So we can compare that to trends in emitted sulfur sulfur goes on to form sulfate particles in the atmosphere, and so they're central for the aerosol effects, anthropogenic aerosol effects. Oh, sorry. So you can see that we had this period where we were emitting a lot of sulfur globally from the 1950s to the 1980s, and then we had this period where the emissions weren't really going up, and that this is when we had this transition from dimming to brightening. And now they've actually started going down. However, if this figure had continued into the present, we would have seen that there's a local minimum actually in right around year 2000. And the emissions have increased again since then. And that increase comes in almost entirely from emissions from China. So, the numbers. Yeah, the numbers are, this is from a paper by Martin Wiltz, and he had, the units are in watts per meter square, but he had compiled that from a number of other papers that had looked at this. All right. So quickly, here are some very recent schematics from the new IPCC report to just remind everyone how aerosols can affect climate. So scattering aerosols have a cooling effect by reflecting more sunlight back to space, and they have a cooling effect both locally and on a larger scale. But there are also aerosols that can absorb solar radiation, and they have a local cooling effect at the surface, but for the entire system and on a larger scale, they actually have a warming effect. And then aerosols can also influence clouds. They tend to brighten clouds by forming more cloud droplets, and so you increase the cloud albedo, and that corresponds to cooling also. So now looking at how these aerosol effects have impacted the radiation budget since pre-industrial times, we're now looking at, from the old IPCC report, the radiative forcings between 1850 and the present. I prefer the old figure for many reasons. One is that I like that the positive forcings or the warmings are color-coded with warm colors, and the coolings have blue colors, which I think is nice. So I wanted to bring your attention to the numbers associated with the direct and indirect aerosol effects here. So the scattering and absorption of solar radiation here, and the effect of clouds here. And now moving on to the newest IPCC report, the forcing diagram looks something like this. And so you can then look at the same forcing numbers from the direct and indirect aerosol effect, and you can see that they've come down quite a bit since the last IPCC report. I always find it interesting that that with the direct effect, we seem to have a high level of confidence about this effect, but it turns out we don't really even know what sign it has. So I'm not sure how you can have a high level of confidence about something that you don't know the sign of, really, but that may be semantics. Anyway, you can see that the error bars associated with the total forcing of climate since pre-industrial times, a lot of those error bars come from the error bars associated with these aerosol effects, and so they are very uncertain. The fact that the total aerosol effect is thought to be somewhat lower now than in the previous report has allowed for a lowering of the range of climate sensitivities that came out of that report. And so I'm going to now move on to a figure that started as a bizarre or maybe a pathetic hobby of mine a while back when I was a graduate student. I started to plot estimates of the aerosol effect that came out in the literature as a function of the publication year. And by now it's become a monster of a figure, but each circle here essentially represents a paper and the estimates that came out of that paper. And I put shadings in here to show what people think is really compatible with the kind of warming we have. So that's sort of the constraint that has become more and more clear, is that the total aerosol effect has to be smaller in magnitude than -2 watts per meter square. So for the aerosol indirect effect in the previous figure, the best estimate for that was 0.55 watts per meter square. So that would be somewhere up here. So you can see that most of the estimates in the literature are actually in magnitude are much larger than that. And the fact that the estimate in the new IPCC chart is so low, I think is related to the fact that they put a lot of weight on satellite estimates that have their own issues. But I wanted to bring in the point that actually most of the estimates that are in the literature give a higher or stronger aerosol effect than what goes into the IPCC chart. All right, so the aerosol effect is uncertain, and that's a problem for us when we try to constrain climate sensitivity. And this was brought to people's attention by Andy Andrea in a paper of his in 2005. The title of that was "Strong Present-Day Aerosol Cooling Implies Hot Future." So we've seen some version of this equation before. It simply relates the radiative forcing since pre-industrial times to the present to the observed temperature change times the radiative forcing associated with a doubling of CO2. And this is essentially the climate sensitivity, the temperature change for a doubling of CO2. And then there's the ocean heat uptake over here that also is going to be addressed in the following talk, I believe. And so you can see that, well, since delta T is measured and known, and we know what the radiative forcing associated with doubling of CO2 is, if for a given ocean heat uptake, we get this inverse relationship between the total radiative forcing and the climate sensitivity. So a large aerosol forcing, large negative aerosol forcing, brings down the total radiative forcing and brings up the climate sensitivity. And that's what Andy Andrea showed in this figure here, where if we have a strong aerosol cooling presently, that implies a very high climate sensitivity. And for a given, these were the old emission scenarios. So for a given emission scenario, if we had a strong aerosol cooling effect presently, that would give us a warming by 2100 of 8 degrees C, which is quite frightening. On the other hand, if we had a very weak or even no aerosol cooling effect presently, that would give a much more moderate warming. So that was one of the perhaps the earlier studies that brought attention to this issue of the strong coupling between the aerosol effect and how it relates to the total forcing and how it relates to climate sensitivity. I'm going to skip that figure because I think it's very similar to what Steve showed. So then a couple of years later, Jeff Keel published a paper where he looked at this relationship in global climate models. And I want to skip back now and say that he used this equation here to come up with the curves in the figure here to say what a theoretical relationship between climate sensitivity and the total forcing will be according to that equation. And then he picked a few numbers for ocean heat uptake for H. And then he plotted for, I believe, 9 global climate models. He plotted that on top of these theoretical lines. And he found that these 9 global climate models fit quite well with that theoretical relationship. And on the right-hand side here is it just shows that what we already know well is that the total forcing is really controlled by what the aerosol forcing is. So when people saw this, they took this as evidence that climate modelers are cheating, because really you can reproduce the temperature record with any kind of climate sensitivity, really, as long as you pick the right aerosol forcing to go with it. And that's true. I mean, the aerosol forcing at this point is so poorly constrained that why wouldn't you pick an aerosol forcing that allows you to reproduce the temperature record of the past? Because you could argue that a very simple test, the first test that you would put a climate model through, is whether it can reproduce the observed temperature record. And in fact, that was the question that Jeff Keel was asking in this paper. He said, how come all these models with all these different climate sensitivities can all reproduce the temperature record of the past? Well, they can do so by just picking the aerosol forcing that allows them to do so. So that's problematic, right? It's problematic that we can't constrain the aerosol forcing better, because that is really what causes the climate models to come up with all these different estimates for climate sensitivity. Well, this is an old study by now, and people have made similar figures for the model simulations from CMIP5. Wow, the simulations that went into CMIP5, and you can actually recognize the numbers or the curve and the dots that went into the Keel figure here in red. And there's a correlation coefficient, R squared, going into that as well. They did the same thing now to see how the CMIP5 models fit with this theoretical relationship. And they published this, and they said, look, climate modelers aren't really cheating, because see that they're not following these curves anymore. Well, then they said, if you take the subset of models that are actually able to reproduce the temperature record of the past to within 90% uncertainty range, those are the symbols here that are highlighted in green. So all the other models really couldn't. The black diamonds here are now from the CMIP5 modeling archive. All these other models couldn't really reproduce the temperature record. And the ones that could still fall on this line, meaning the models that reproduce the temperature record are still, compensating. If they have a high climate sensitivity, they need to have small forcing, meaning a large negative aerosol forcing. So this is still true. So how do we make progress? The climate models haven't been really able to constrain the aerosol effect, and therefore they haven't been able to constrain equilibrium climate sensitivity better either. And so that's where this, and I wanted to, actually I'll skip that. So that's where this new approach that I've taken with economists, with Peter Phillips and others in the economics department, that's where this new approach comes in. So we've taken a major step back, and we started out with a simple energy balance. We started out with the principle of energy balance, taking into account the radiation budget and heat transport within the system. And we've come up with this equation for the temperature at a time t plus 1, where t is in years, at a given location. And we find that can be related to, based on these energy balance principles, that can be related to the temperature of that location in the previous year, the radiation that reached the surface at that location, solar radiation that reached the surface at that location in the previous year, and then a global term. And the global term has global temperature, global radiation reaching the surface, and CO2. And so we have 1,300 locations where we have constructed this equation here, and we feed it observations for each of these locations. So the observations are incoming solar radiation from this Global Energy Balance Archive, the GEBA data set, that has been measuring solar radiation reaching the surface with instruments around the globe, going back to the earliest measurements start in 1920, but we were really able to get good coverage only after 1964. So our analysis starts in 1964. We also have temperature data for each station from the HADCRU data set, and we have equivalent CO2 data from the annual greenhouse gas index. And so what we've done is, for the 1,300 equations that we had for each location, we fed these observations into these equations. And we try to determine these coefficients here, and that's where my collaborators in the economics department come in, because they then use dynamic panel data methods to determine these parameters that would allow us to agree as well as possible with the observed at all these 1,300 stations simultaneously. And so after calculating the values of these parameters that would allow us to do that as well as possible, we came up with this decomposition of the observed temperature from 1964 to the present. And so that equation with the estimated parameters is that purple curve here, and observations for each individual year are in dots here. And you could argue that the simple approach with the fitted parameters do a decent job, at least as well as global climate models, I would argue. What you can also do then is with that same equation, you can set CO2 constant at 1964 values and only allow radiation to change. Oops, I'm sorry. And you get this cooling because of this period where you had dimming. You had downward trends in solar radiation. And then as you transition to a stabilization, you don't get much of a cooling anymore from aerosols. And then you can do the same thing by setting radiation constant at 1964 levels, and then you get a much stronger warming than what you actually got with a combination of aerosols and greenhouse gases. So that way we could decompose the temperature trend into a contribution from aerosols and a contribution from greenhouse gases. I really want to emphasize that we don't think of this model as anything that has predictive abilities. We wouldn't dream of using this to predict the future, but we think of it as something that could be used to try to understand the past. What you can also get out of this very simple approach is you can get out of this a climate sensitivity. If you get gamma 3, you get the sensitivity to equivalent CO2. Okay? So we get this transient climate sensitivity from gamma 3 times log 2. And that gives us a transient climate sensitivity of 3.4 Kelvin. Note, however, that you can only think of this as valid for the part of the world where you have stations. And essentially, you could think of it as valid for land only. And there's a 95% confidence interval of that goes from 2 Kelvin to 4.8 Kelvin. You could argue that temperature change over land is much more relevant for policy than global mean temperature change. But if you wanted to translate this into a global mean transient climate sensitivity, we can use the information that we have from the temperature record, knowing that land has warmed roughly twice as much as the oceans in the temperature record, in the recent temperature record. So then you can translate that into a global transient climate sensitivity of 2.2 Kelvin with a confidence, 95% confidence interval going from 1.3 to 3.1 Kelvin. So I put that into this. You'll recognize this figure. You've seen it several times today. It shows the various estimates of transient climate sensitivity from the last IPCC report. And I put our study here. And you can see that our best estimate is at the upper range of what the CMIP5 models, for example, predict. So the black histogram here is from the CMIP5 models. And our estimate is really at the upper range of that. And it's much higher than, for example, the recent paper by Otto and coworkers in Nature Geoscience, where they came up with a best estimate of 1.4 Kelvin for the transient climate sensitivity. So this is a purely observational-based approach to estimating the transient climate sensitivity that I'd love to have your feedback on. Finally, I wanted to, I know I'm over time. I wanted to just talk briefly about the sensitivity to the choice of time window, because there have been some studies coming out recently that found a lot lower climate sensitivity when they took this recent period of the hiatus into account. So we wanted to see if we, instead of that full 46-year time period, we chose a 25-year rolling window. What kind of transient climate sensitivities could we get from that? And so if you choose this time period going from roughly the 60s to the 80s, you get somewhat lower climate sensitivities because you had this period where it wasn't really warming much. So then you get lower climate sensitivities. Then you move into this period where we got accelerated warming, and you get these higher climate sensitivity estimates. And then if you choose the most recent period, you get something in between. And for the full period, you see the the distribution that comes out of that rolling window approach. And that brings me to my conclusion. So there is this intimate relationship between aerosol cooling and climate sensitivity. And it's a problem that we can't constrain the aerosol effect better, because that means that we can't constrain climate sensitivity better in our models. And then finally, this new approach that we've taken, the simple approach, gives us a transient climate sensitivity of about 2.2 Kelvin. And it supports the higher transient climate sensitivity estimates that came out of CMIP-5. And then finally, I put this here as a reminder for us all working on climate sensitivity to do the press release after we've had our papers go through peer review. Some of you may have seen this in The Economist, where they published on some papers by Norwegian colleagues of mine, actually, and the papers have still not gone through peer review, and this was it was early this year. So with that, I'll end and take questions. Or actually not. Questions later, right?